So the first thing that I see on page 19 is that it wants to discuss mean, median, and mode. Mode is very simple. Mode is the value that occurs most frequently. A modal class is the class with the highest frequency. So if I have something like this in a histogram, this would be the modal class. If I was forced to pick a mode, it would be the midpoint of that class. So this would be the mode. This would be the modal class in a histogram. Meaning the class meaning bar, right? The bar that occurs most frequently. It talks about two different means. This is the sample mean, x bar n. The subscript tells you how many in your data set. Mu, of course, is the population mean. This is a parameter. This is a statistic. The formula is the same for both, with capital N replacing lowercase n if we're talking about the parameter mu. Right? Just add them all up and divide by n. So today I want to talk about your page 3 in the class notes. This is page 3. It talks about the fact that the mean is not robust. It says, is the mean robust? The answer is no. Robust means stands firm in the presence of outliers. So what I've done here is I'm attempting to show you an example where the first example has 10 $50,000 salaries. This one right here is the same data set as before, only I have added an 11th salary of 500,000, which is an outlier. And I want to see what happens when I add an outlier. What happens to the mean when I add an outlier? So if I have 10 $50,000 salaries, or roughly $50,000 salaries, then obviously the mean is 50,000 because I added up 10 of them and then I divided by 10, so obviously the mean is still 50,000. Here, however, when I have 11 salaries with 10 of them being 50,000 and the 11th one being 500,000, look what happens to the mean, x bar 11. Not only do I have the 500,000, but I have another 500,000 because it's the sum of the 10 $50,000 salaries. And so it's $1 million divided by 11 data points. I'm taking the mean, so I'm doing summation xi divided by n. So I get 90,909 as my mean. So as you can see, just including one large data value of 500,000 has made the mean practically double. So that kind of clues us in to the fact that mean is not really appropriate for talking. It's not appropriate to talk about the mean when we're talking about data sets with outliers because it misguides you. Imagine if you went on a job interview and the guy told you that the average salary, the mean, was $91,000. Is he lying? Is he lying when he says that the average salary is $91,000? He's not lying. The average is $91,000. Does that mean that you're going to be earning $91,000 next month when he hires you? No, because the $500,000 salary is his salary and everybody else is earning $50,000. So although he's not telling an untruth, it's not a lie, but it's not appropriate to talk about the mean because it will give you bad results, right? It gives you an average of 91,000, and that's nowhere near the center of the distribution. So it proves to you that the mean is not robust and jumps around like crazy with the inclusion of simply one data value, which is 500,000. So the median would be more appropriate. Look at the median when you have 10 data values. The median is the middle score. So that would be the average of the 5th and the 6th, but both of those happen to be 50,000, so the median is $50,000. And here also the median is 50,000 because when you have 11 data values, the middle score is the 6th one. So you have 5 and 5 and on either side, and the 6th one is still 50,000. So the inclusion of a $500,000 salary does nothing to the median, showing you that the median is extremely robust and should be used when there are outliers. Follow me? Okay, so the next paragraph here on page 3 is talking about these rules on the bottom of page 19. Do you have this in front of you? So that I don't have to keep zooming in and out, in and out. Do you have this in front of you? The first rule says, if yi is equal to xi plus c, I going from 1 to n, here. If yi equals xi plus c, I going from 1 to n, then y bar is equal to x bar plus c. So what is that saying in words? It's saying if you start with a data set like this, I start with a simple data set. It only contains 3 numbers. Oops, sorry. It only contains 3 numbers, 3, 4, and 5. And if those are my xi, okay? 3, 4, and 5. I want to create another data set y, which is obtained from the x data set by adding a constant to every value. So I'm adding 10 to every value. And now I have 13, 14, and 15. Well, the old mean x bar 3, the subscript, of course, telling you how many data points you have in your set. So x bar 3 is the sample average of these 3. That's obviously 4, because it's the middle one, right? They're equidistant. 3 and 5 are equidistant from 4, so the mean is going to be 4. And the new mean is 14, which is exactly 10 more than 4, showing you that if you add 10 to every one of the data points, you don't have to recalculate the mean here. It's just the old mean plus 10, right? And the same thing applies for multiplication. So that's the second rule here. If yi is equal to c times xi, then y bar is equal to c times x bar. So I did exactly the same thing, only this time multiply by 10. So I started with 3, 4, and 5. I multiplied everybody by 10, and it's obvious to see that the old mean was 4 and the new mean is 40. So the new mean is exactly 10 times the old mean. It doesn't need to be recalculated. And then the next one says, right here, if yi is obtained from xi by multiplying by c1 and adding c2 to that, then the same pattern will be followed by the means. So y bar would be c1 x bar plus c2. So I just illustrate that by first multiplying by 10 and then adding 100 to every single data value. The old mean was 4. The new mean is 140. So it's obtained by multiplying the old mean by 10 and adding 100, the same pattern that I did to every single data value. So this is not some big mystery. It's saying that the mean will follow the same pattern that you did to every single data point. So on your exam, if you're given a bunch of data and it says, I would like to multiply everything by -5 and then add 5 to the original data, you're just going to do it to the old mean. You're going to do that pattern to the old mean. You will not do that to every single data value. Agree? Okay. I'm here. I want to talk about measures of dispersion, measures of variance. The first one being standard deviation. Do you guys know about variance and standard deviation? Is there anyone who does not know? Does not know about variance or standard deviation? Which is bigger? Variance is the square of the standard deviation. So the variance is defined to be the mean of the squared deviations. So let's say you have a bunch of values like this, right? 3, 6, 4, 9, and 8. Let me put the notes up so that you can see what was written before. Here's page 7 of your class notes. I'm here. Do you guys know what mid-range is? Have you seen that before? Mid-range is different from range. Range is max minus min, whereas mid-range is min plus max over 2. Understand that this is plus. It's the average of the min and the max. It's different from the range. Or it's not half the range. That's a standard trick question, right? Mid-range equals half the range, and the answer is false. It's not. It's the average of the min and the max. Anyway, we were talking about variances. So when you take your first exam, when I report the scores to you, I might say to you the average was an 80 with a standard deviation of 3. What does that mean? That means that on the average, the score varied from the mean by 3. On the average score differed from the mean by 3. That's what that means. So how would I come up with that standard deviation? Let's say I have a bunch of values like this, 3, 6, 4, 9, and 8, and I'm looking for the standard deviation. There is no way to get the standard deviation unless I go through the variance, where the variance is defined as the mean of the square of the deviations. The reason why I have to square the deviations is because if I didn't, some values would be larger than the mean and others would be less than the mean, and the positive deviations would cancel with the negative deviations, and I wouldn't get any results. So for that reason, we square the amount by which a number differs from the mean, and then in the end you're going to take the square root to give you the standard deviation, like you see me doing here. Do you understand what I'm talking about? For example, if I had 3, 4, and 5, right? I couldn't talk about the deviation from the mean because this deviation would be negative and this deviation would be positive, and this -1 and the +1 would cancel, and I get no results at all. Follow me or no? Did I lose you? Did I lose anybody? So first I need to take my data, 3, 6, 4, 9, and 8, and I compute the mean of that data set. Because when you talk about deviations, you're talking about how much does the data vary from the mean, deviate from the mean. So the first thing I do is find mu, which is the population average, add them all up and divide by 5 because I have 5 data points here. So I get 30 divided by 5, which is 6. Next, I will create a column of deviations from the mean. So xi minus mu is your first column. So 3 minus 6 gives me -3, and 6 minus 6 is 0, and 4 minus 6 is -2, 3 minus 6, 9 minus 6 is 3, and 8 minus 6 is 2. So now I have a bunch of deviations. The sum of this column is always 0. If it's not, it means you found the wrong mean or you've subtracted wrong to find one of the deviations is wrong. Next, you square these so that the result is always positive. So I get 9, 0, 4, 9, and 4. And since the variance is defined as the mean of the square of the deviations, I need to take the mean of these numbers. These are the squared deviations, and I need to find their mean. So how do you find the mean? You add them up. I get 26, and then I divide by 5. So 26 over 5 is 5.2, and that's the variance. The variance is denoted by lowercase sigma squared. Sigma squared. That's the variance, the population variance. And of course, if I want the standard deviation for the population, I simply take the square root of the variance. So radical 5.2 gives me 2.28. So on the average, the data varies from the mean of 6 by 2.28. That's what this is saying. Follow me or not? That's how you find the population standard deviation, sigma. On the other hand, if we're not talking about a population, but rather a sample, the formula would change. Here's the formula. Sigma squared equals summation xi minus mu square over n. Because that's what I did. Look, I found the deviations column xi minus mu, then I squared them. So I had xi minus mu square, and then I divided by 5, which was n. So this is my formula for sigma squared, and the formula for sigma would just be the square root of this quantity. Let me know what your question is before I turn the page and move on. Can you find me right now the standard deviation of 4, 5, and 6? Can you? Would you do it right now? Do it. I want to see the work. I want to see xi minus mu square. Sigma squared equals, sigma equals. Do it. So I'm talking about 4, 5, and 6. What's the mean? Yeah. So I create a column of deviations, xi minus mu. This is my deviations column. So 4 minus 5, 5 minus 5, 6 minus 5. Add them all up, you get 0. You must get 0. Next one is xi minus mu square. Square them, you get 1, 0, 1. Add them, you get 2. So the formula is sigma square, that's the variance, equals summation xi minus mu square divided by n. My n is 3. So I get 2 divided by 3. Are you with me? Yeah.
Why is it that in this case the standard deviation is not what it actually shows in the data points?
Why do you say that? This is the variance, not the standard deviation.
Oh, okay.
This is the variance. Right? The sigma would be the square root of 0.66. 0.6 repeating.
Where's the 3 from?
3 data points. N is 3. 4, 5, and 6. 3 points. Get it or no? What's your question, folks? So I don't memorize this. I just remember the definition. It's the mean of the squared deviations. So find the deviations, square the deviations, find the mean of them. Yeah.
Is the standard deviation supposed to be 1 in this case?
Why would it be?
Because you said it's the average score away that the other scores are.
Did you count the 5?
Oh, so you have to count the 5 also.
Shouldn't you?
But it's 0, so why would it?
Because the first point differs by 1, the second point differs by 1, and the third point differs by 0.
So that drags it down.
So it'll drag it down, yeah, and it did. Get it? Okay, so the picture changes slightly if I'm talking about a sample. Here I'm talking about a population standard deviation, sigma, right? It's slightly different if you're talking about a sample. S squared is the variance for a sample, and it's summation xi minus x bar square over n minus 1. Slight difference in formula. This formula has an n in it. This formula has an n minus 1 in it. This is due to Bessel's correction. This is Bessel's correction. So Bessel said that when you have a large, Bessel said a lot of stuff. I'm going to tell you everything that he said. So first reason for this being n minus 1 rather than n is because when you have a large population and you're trying to find sigma, you don't have the patience to go through each value and find the deviation and square the deviation and then take the mean of the deviations. So you will take from amongst this population a representative sample like this, x, 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 x. So let's say I take this as a sample. And here's an outlier which got left out and wasn't included in the sample, perhaps. What is the effect of an outlier on the standard deviation? Does it matter if the outlier is on the low side or the high side? Does it matter? Yeah. Yeah. So just like the mean gets thrown off by the outlier, so does the standard deviation get thrown off by the outlier. Are you with me? Let me stick an outlier in here to show you what happens just for a second, okay? Because I think it'll help you in the long run. So let me change some values here. Let's say that instead of this being a 6, this is a 36, suppose. Let's see what happens. First of all, what's the mean? What's the new mean? 36 and 5 is 41. 41 plus 4 is 45. 45 divided by 3 is 15. So the new mean is now 15. Let's take the deviations from the mean. So 4 minus 15, negative 11. 5 minus 15, negative 10. 36 minus 15, 21. Do they add up to 0? Yes, they add up to 0. Let's square them. 11 squared is 121. 10 squared is 100. And 21 squared is what? 21 times 21. What is it? 21 times 1 is 21. 420. 441. Yeah? 441. Add these up. What do you get? 541, 662. 662 divided by 3. 221, let's say, just for round numbers, right? And I want the square root of that. How much is that, roughly? Square root of 225 would be 15, right? 15 times 15, how much is that? Hello? I must have 100 people here. Can anybody tell me the square root of 221, roughly speaking? Isn't 15 times 15 225?
14.86.
Okay, so let me call it 15, right? Roughly speaking. Sigma equals 15. So I added one outlier of 36, and it made the sigma go absolutely crazy. The sigma was less than 1 before, right? And now it's 15. So do you think the sigma is robust? Robust means stands firm in the presence of outliers. So absolutely not robust, right? So I get back to this question here and Bessel, right? So Bessel said, if there is an outlier in the population that wasn't included in the sample, after all, the goal of the sample standard deviation is to draw estimates about the population standard deviation. The whole reason why you take a sample is because of inferential statistics. You don't know what the population standard deviation is, so just draw from amongst the population one random representative sample, and whatever you get for S will be used for sigma, because you don't have the patience to find sigma or the resources to find sigma. That's the story here. So if this outlier was not included in the sample, it means that the value for S that you will get from your sample will be an underestimate of sigma. Do you agree with that? Because the outlier wasn't included, was not included, which means whatever number you get is going to be too low because the population actually contains outliers, but your sample didn't. So whatever value you get for S should be bumped up, because if you don't bump it up, it doesn't account for possible outliers in your population. So I choose to bump this up by dividing by a smaller number, n minus 1, rather than n. Yeah?
What if you have a data set with high numbers and then the outlier is low?
That's okay, because the outlier, even if the outlier is lower, the deviation will be negative if the outlier is lower. But when I square it, it'll still be positive. So whether the outlier is on the left side or the right side of the mean doesn't matter, because its impact will be exactly the same because of the squaring. So it'll still throw off the standard deviation by the same amount, whether it's on the left side or on the right side of the data set. Follow me? Okay. So my goal is to increase the standard deviation by dividing by a smaller number, n minus 1. So what you probably should be saying to me right now is, why n minus 1? Why not n minus 2 or 3 or 4 or some other number? Why n minus 1? And the answer is due to Bessel. Bessel said that the degrees of freedom are n minus 1. So two more things to say about this n minus 1. N is the number of independent data points. The number of independent data points. And 1 is the number of parameters estimated along the way. Estimated along the way. Let me explain. So when I have 3, 6, 4, 9, and 8, and they belong to a sample, I have 5 independent data points. And one parameter was estimated along the way because this x bar is itself an estimate of mu. Because I did not look at every single data point here and calculate the mu from every single data point. X bar is just the sample mean of some random sample that's chosen. So one parameter, mu, was estimated along the way. So the number of independent data points minus the one parameter gives you the number of degrees of freedom for this estimate. The number of degrees of freedom is the number of independent data points minus the number of parameters estimated along the way. That's why it's n minus 1 and not n minus 5 or something like that. The other way to look at this is that because I have a constraint here, that this sum always should be 0, all but one of them are free choices, but the last one is not a free choice. One of them is not a free choice. I have n minus 1 free choices because I'm working with the constraint that says that summation xi minus x bar, or mu, whatever you're talking about, should always be 0. So a missing value here is never a free choice because all of them have to add up to 0. So if this were missing, it would be forced to be 21 because the sum of the others is minus 21. So I have n minus 1 degrees of freedom in this estimate of x bar. So for many, many reasons, most of them due to Bessel, this number is now n minus 1 when you're talking about a sample variance. So S squared is the sample variance, and S is the sample standard deviation. That is just the square root of this above quantity, xi minus x bar squared over n minus 1. Follow me? So if I were to find the S for this, everything would remain the same. Let me just do it, okay? So if I had 4, 5, and 6, if I had 4, 5, and 6, and these were my xi, and the first thing I would do is find x bar, which is still 5. So xi minus x bar, the deviations would still be negative 1, 0, and 1. And xi minus x bar squared would still be 1, 0, and 1. When I add them, I still get 2. So my formula is this. S squared equals summation xi minus x bar squared over n minus 1. So this time it would be 2 divided by 2. Not 2 divided by 3 like it was before. Because this is n minus 1, 3 minus 1, which is 2. So I get s squared equals 1 and s equals 1. Because it's the square root of 1, which is 1 also. So s is bigger than sigma, just as I intend it to be. Follow me? For many reasons, as we said. What's your question regarding what I've done? Anything at all? So let me ask you this. If I have two distributions that look like this, here's one distribution and here's another distribution. Which has a higher standard deviation? Actually, I have 15 values. I probably should make 15 values in the other one too, right? Because this is 3 times 5. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Which one has the higher standard deviation? Yeah. She says the first one. Do you agree with her? How many agree with that? The first one. And how many say the second one? Nobody says the second one at all? I want the larger standard deviation. Why do you say the first one?
Because there's greater variance as opposed to the second one where it's 3. If you look, it's going up like the same pattern. I don't know if that makes sense. I don't know if it's right next to it.
The first one varies more? Varies more? First one? Go ahead. I disagree with you. I'll explain.
Are they the same?
I don't think so.
Okay. I just didn't know if with the average and all the sample sizes being the same, came out to the same.
So let me back up, okay? What is standard deviation and what is variance? What is it telling you? On the average, how much does the data vary from the mean, right? So when I ask you, who has a larger... Go ahead. The second one has a higher standard deviation. What about variance? Same? Or no? If it has a higher standard deviation, it has to have a higher variance, right? Because it's just a square. The variance is just the square of the standard deviation, right? So the question is, why does this one have a high standard deviation? Yeah. Bingo. Which one has more points away from the mean? When we say which one deviates more, we're saying deviates from the mean. So look at this, right? I have 5 points that don't deviate from the mean at all. So they contribute nothing to the deviations from the mean. Here I have 3 that deviate 0 from the mean. I mean, they're not any far further than the mean. The mean is here and they're here. So they contribute a 0 to the deviation column. You understand where I'm going? Look at these now. This one has 3 that deviate by a distance of 1 on one side of the mean. This one also has 3 data points that deviate by a distance of 1 from the mean. But then this one has 2 that deviate a distance of 2 from the mean, and this one has 3 that deviate a distance of 2 from the mean. So doesn't this deviate more from the mean than does this? Yes or no? Another way you can look at the same thing is that I have taken this and brought them, this guy brought it here and this guy brought it here. Doesn't this now deviate more from the mean than before? Because these 2 x's before did not deviate from the mean at all because the mean was here. And now they deviate a distance of 2 from the mean. So which picture deviates more from the mean, this one or this one? Are you guys not understanding me, or is it understood and you want to move on? Yeah.
So are we looking at these as 5 groups of however many in each column?
So there are 5 different values for this data, and these 3 are the same. So like this, 1, 1, 2, 2, 2, 3, 3, 3, 3, 3, 4, 4, 4, 5, 5, for example. And this one would just be 3 of each number. So I'm asking who deviates more from the mean. So I'm saying one quick way to look at this is to say, I had some distribution here, and this data point now is not a 3, but rather a 5. So this 3 becomes a 5, and this 3 also becomes a 5, and all of a sudden I have this data set. So it was a 3 before and contributed nothing to the deviations from the mean because it was sitting at the mean, because the mean is 3. But this one deviates a distance of 2. These all deviate distances of 2 from the mean. So moving these out and making the picture flatter, shouldn't that make things deviate more from the mean? So basically, this is the question. Does this have a bigger standard deviation, or does this have a bigger standard deviation? They both have the same mean.
So what you're saying is that the more points you have that are not the mean itself makes the standard deviation higher.
Exactly. Exactly. The further you are from the mean, and the more points you have like that, makes your variance and consequently, your standard deviation go up. So here I have a whole lot of data. In this picture, I have a whole lot of data. Look at the area under the curve, close to the mean. And by close, I mean less than or equal to a distance of d from the mean. Whereas in this picture, the flatter picture, this is the only area right here within a distance of d from the mean. And all this stuff right here varies greatly from the mean. So wouldn't the flatter picture have a larger variance from the mean? Variance is all about varying from the mean. Yes or no? Is it crystal clear that 2 has a larger variance? Yeah? Okay, I move on.